Hi everyone, we're going to talk about basic chemistry. In your course pack, I'm starting off on page 4. If you're new to chemistry and have not had a course previously, these are some of the terms that we'll discuss throughout this chapter. There's no need to memorize this list or their definitions. Rather, I would encourage you to work through these terms as we work through these PowerPoints. Let me start you off with a definition for matter. Matter is defined as anything that takes up space and has mass. We say that matter is composed of atoms. Atoms of the same type compose elements. That's where we're heading here. We're going to talk about atoms and their relationship to elements. This is the periodic table of elements. There's over 100 that you can see here. We're only going to talk about the ones relevant to the human body. The elements that you'll want to be familiar with are these listed in the chart on the bottom of page 4. You'll want to know the symbols for these elements if that's something you're unfamiliar with. You'll also want to know that the top 4 elements are oxygen, carbon, hydrogen, and nitrogen. Sometimes they also include 2 others, phosphorus and sulfur, as the top 6. I've had students before rearrange these letters. Oxygen, carbon, hydrogen, and nitrogen can rearrange as HONC, H-O-N-C, and if you include the top 6, they are rearranged as New Hampshire cops. Nitrogen, hydrogen, carbon, oxygen, phosphorus, and sulfur. So kind of a fun way to keep that straight. Now the others listed here are considered trace elements. Everything from calcium, potassium, sodium, chlorine, magnesium, iron, and iodine are considered to be trace. That means they're found in smaller amounts in the human body. You'll want to look on your sheet on page 4 at what the general role for each of these elements is in the human body and familiarize yourself with that. These are things that we'll discuss throughout both Bio 210 and 211. Hey, just a caution about learning this list of symbols. If this is new to you, just be aware that some of these symbols do not match the name of the element. For instance, K is the symbol for potassium. That's based on its Latin name. Sodium has Na for natrium, its Latin name. So just a heads up there. If you'll flip on over with me to page 5, let's talk about atoms. We know that atoms of the same kind compose elements. That means that if you have an element like oxygen, all the atoms there have some similar characteristics. And these characteristics are based on the 3 subatomic particles that we're looking at next. You'll want to take a moment to pause this video and write down in your box there on page 5 the 3 subatomic particles, their charges, and locations in the atom. We know that both protons and neutrons are housed in the nucleus. That is the central portion of the atom. Protons carry a positive charge, while neutrons carry no charge. They're considered to be neutral. The electrons are considered negative. They are orbiting the nucleus. So just keep straight that neutral and neutron go together. Electrons are in fact the negatively charged particles here. Let's talk about what you see in these 2 pictures. Let's take the atom on the left. The atom on the left has 8+. That plus there illustrates that we're looking at positively charged protons. This little symbol here implies that we have neutral charged neutrons. So there are 8 positively charged protons and 8 neutral neutrons there. In the atom on the right, we have 10p, that stands for protons, and 11n stands for neutrons. So this structure here is just representing the nucleus, although they're just housed in the central portion of the atom. Let's talk about the orbitals that you see here, where the electrons reside. The orbitals can hold a certain number of electrons depending on what the size of that orbital is. In this course, I'll use the terms orbital and shell interchangeably. If you've had a chemistry class, you may know those have slightly different definitions. So in each of these pictures, you'll notice there are 2 electrons in the innermost orbital or shell. That little innermost orbital is very small, and that's all we can hold there are 2 electrons. And if you've got 2 electrons there, then you've satisfied a rule. That rule would be called the duet rule. Just like if you sing with another partner, it's called a duet. Here, that would be called a duet rule. Now, if you spill over with more electrons, you may have to fill up another orbital. And if you do start filling up another orbital, then you may, in fact, have 8 there. And if you do put 8 in that next orbital, then you've satisfied what we call the octet rule. Let me tell you something about this particular orbital. See, this one here is the first one closest to the nucleus. This one here is the second one. It's further away from the nucleus, so it has more room. Because it's bigger, we can hold up to 8 electrons there. 8 also happens to be the number that satisfies our octet rule. This outermost orbital also has a special name. The outermost orbital is always called your valence shell. So I'm going to be looking at our valence shell as we look through some examples in the next few slides. Let's look at the valence shell here. Remember, the valence shell is the outermost orbital, and I'm looking to see if there's 8 electrons there. Why 8? Well, 8 would mean that we have satisfied what rule? The octet rule, right? So just check for a moment and see if we have 8. I believe we will have 8 out there. So I will say that we have satisfied the octet rule, and that means that we have a stable atom. Stable atoms are ones that are not going to be willing to share or transfer electrons, or stable atoms are ones that have been created through the transfer or sharing of electrons. So we'll talk more about what exactly that means as we come through the next few sets of slides. So in fact, both of these are stable atoms. They have 8 electrons in the valence shell, and that satisfies what rule? That satisfies the octet rule. Okay, so that takes care of this term down here. Let's now talk about the word neutral. Neutral atoms are those that have the same numbers of protons and electrons. Remember that protons carry what charge? Positive. And electrons carry what charge? Negative. So we're going to assume that all of the elements on the periodic table are in fact neutral. So just take a moment to count the charges here. In the nucleus we have 8 positive protons, but count both orbitals, count all of your electrons. I come up with 10 electrons. So we do not have a neutral atom on the left. We would say it's not neutral. In fact, it's a cation or an anion. Those are terms we'll talk about later too. On the atom on the right, count your positive protons, count your negative electrons. I have 10 positive protons and 10 negative electrons. Because those numbers are the same, I will say that I have a neutral atom on the right. So let's find a place to jot that down. This one is neutral on the right. This one on the left is not neutral. Okay, so we'll do this again so we have an opportunity to practice this on some more pictures. So let's together draw an atom with 8 protons, 8 electrons, and 9 neutrons. Please pause and go ahead and draw that in your notes, and then resume this when you've had your drawing completed. All right, so let's take a look at the nucleus. We know the nucleus has 8 protons. I'm going to use 8 positives there. We know 9 neutrons go in that, so I'm going to put the little no charge symbol there. So let's now focus on these electrons. How many electrons go in the innermost orbital closest to my nucleus? Only 2 can fit there. Okay, that means that I've filled up that innermost orbital, and I now need to spill over and create a second orbital. Since I've taken care of 2 of those 8, how many more do I need to distribute on this next orbital? Let's place 6 out here. Now, you'll notice that I'm putting a negative symbol and I'm circling it. That is just habit, because the negative symbol reminds me that these are negatively charged electrons. So, where's my valence shell? Is it the innermost orbital or the outermost orbital? It's your outermost orbital. Now, I'm interested in seeing if my valence shell satisfies the octet rule. So the octet rule means that we need 8 electrons in order to be stable. Do we meet the octet rule here? Nope. That's because we only have 6 in that valence shell, and to meet the octet rule we would need 8 electrons. So I actually have room for 2 more electrons to sit on that valence shell. Let's also talk about this neutral issue. To be neutral, I would need the same numbers of protons and electrons. I have 8 of each, so yeah, this is in fact a neutral atom. It's just not a stable atom. Let me give you a moment to draw this atom with 13 protons, 13 electrons, and 12 neutrons. Okay, so in the nucleus, we're going to place 13 protons and 12 neutrons. And let's draw our first orbital here. How many electrons can it hold? Well, it's only going to be able to hold 2 because it's a rather small orbital. That means I've taken care of 2 out of the 13. I need to put another orbital here, and this one can hold up to 8. Now, let's talk about this orbital for just a moment. This orbital is full with 8. This orbital also is stable with 8. Just happens to be magic that way, right? This second orbital is full with 8 electrons and it's stable with 8. So it just happens to satisfy that octet rule. So now I've taken care of, 10 total electrons, and I have, 3 left to distribute. So let's draw another orbital. And how many should I put on this orbital? Let's put 3 out there. And you want to confirm that we've got 2 in the innermost, 8 in the next, and now 3 in my valence shell. So that takes care of our 13 electrons. So we know this outermost orbital is our valence shell. And of course, the question I'm going to ask is, does it satisfy the octet rule? With only 3, it does not. So we don't satisfy the octet rule. And what does that tell me? That tells me this is not a stable atom. In fact, it's a reactive atom, meaning that it's going to be looking for a way to get rid of those 3 electrons or gain 5 in order to create stability. That's kind of the topic of chemical bond formation. Now, I want to tell you about this outermost orbital. It is still stable with 8, okay? So if it has 8, it will be stable because it will satisfy that octet rule. But this orbital can hold up to 18 electrons. So even though only 8 creates stability, we can hold many more. In fact, if we had another orbital around the outside here, then that one would still be stable with 8, even though it may hold even more than 18. All right, so let's talk about our other issue, which was neutral. And we look at the numbers of protons and electrons. They are, in fact, the same here at 13. So yeah, this is a neutral atom. It just is not a stable atom. All right, one last one for you to try. 14 protons, 14 electrons, and 15 neutrons. Let me give you a moment to draw that one out. All right, in the nucleus, we're going to place our protons and neutrons. In our first orbital, we're going to place 2 electrons. That's 2 of the 14 we've taken care of. Well, we've got more to place, so let's put 8 here on the next orbital. All right, so now I've taken care of, 10 total. And then how many do I place on my valence shell? Valence shell just means outermost, right? And that outermost shell holds, we've only got 4 there, so it holds up to 18. And what is our magic number for stability? That would be 8 electrons. So we fall short of meeting that goal of only having 4 in that valence shell. So just to review, the way you fill the orbitals of an atom, you place your innermost orbital holds 2, and that in fact means that we've satisfied the duet rule. The next orbital can hold a maximum of 8, and if it in fact is full, then we've satisfied the octet rule. The third orbital holds a maximum of 18 electrons, but only 8 is required to satisfy the octet rule and create a stable atom. We won't work with any electrons or atoms here above the third orbital, so that's as far as we'll go in terms of talking about stability. So just to review, the way you know if an atom is stable, which is considered to be inert or not reactive or reactive, then what you're looking for is the valence shell. If you have only the innermost orbital and you have 2 electrons, then that means that we have satisfied and met the duet rule. Stability has been achieved. If you have a second orbital, third orbital, or so on, then you're looking to see if that atom meets the octet rule. Now, how many electrons should we find in the valence shell if we're looking to satisfy the octet rule? We're looking for 8 electrons. So take a look at these 2 examples. On the left, that atom has reached the duet rule because of 2 electrons in the valence shell, so it's stable. The atom on the right Count that valence shell. Only 6 electrons out there means that this is a reactive or not a stable atom. That means that it's too short of that octet rule. So here, let's take a look at the valence shell. The valence shell, of course, is the outermost orbital. And we're going to count to see if there's 8 electrons out there, and it looks like there are. So yeah, we've met this octet rule. So would you consider this to be a stable or a reactive atom? This one is stable. Take a look at these two examples here. Which one of these is stable? Well, that is the atom on the left, and if you take a moment to count those electrons, there are in fact 8 electrons in that valence shell. So this one is a stable atom. How about this one on the right? It only has 4 electrons in the valence shell, so this one is considered to be reactive. So now we're going to switch gears. If you follow me over to page 6, we're going to talk about atomic numbers, mass, protons, neutrons, and electrons. I'm not going to read this list of rules to you, but they are posted in your course pack on page 6, middle of the page. But we're going to instead work through these using some examples. First of all, the atomic number is kind of like the social security number of an element. The atomic number is indicative of the number of protons and atoms in that element. So when you're looking at this snippet here of the periodic table, there's 2 numbers. The smaller of the 2 numbers is always your atomic number. It's, like I said, the ID number for the atoms in that element. Let's pick on calcium down here. Calcium has a 20. That 20 is the atomic number. And that number, of course, tells me how many protons that I have in an atom of calcium. Now, that's always going to be 20. It's never going to change. If you change the number, like if you take a proton away, look what happens. You've got a different element. So you're never going to see that proton number change. If you do, you're moving around the periodic table. Let's pick on sodium for just a minute. Sodium has an atomic number of 11, and that tells me that we have how many protons? That means you got 11 protons. Now, we're going to assume that the periodic table shows us neutral atoms. And just a reminder, what does the word neutral mean? Neutral means equal numbers of protons and electrons. So if I assume that we have an atom of calcium and it has 20 protons, and we assume it's neutral, I'm going to assume that there are equal numbers of protons and electrons, both being 20. So that makes our job a little bit easier. Let's pick on sodium for just a moment. Sodium has 11 as its atomic number. That tells me we have 11 for the number of protons, and the number of electrons is also 11. Let's do potassium down here. Potassium has an atomic number of 19. How many protons and electrons? 19. Okay, so we're assuming that all of these elements and their atoms here on the periodic table are neutral, meaning they have equal numbers of protons and electrons. Let's talk about the mass number. The mass number is the weight of the atom, and it goes off of the protons and neutrons that are housed in the nucleus of that atom. Let's pick on carbon for just a minute. Its number is 12 here. Now, if you've had a chemistry class, you'll know there's a difference between atomic mass and atomic weight. For here, we're going to use those terms to mean the larger of the 2 numbers on the periodic table. So the mass equals the number of protons in the nucleus added to the number of neutrons. So here for carbon, it happens to be 12. The mass number for nitrogen is 14. How about the mass number for oxygen? 16. What is the atomic number for oxygen? It's 8. What about the number of electrons in an oxygen atom? 8. How about the number of protons in a nitrogen atom? That's 7. P stands for phosphorus. What does 15 tell us? There are 15 protons. There are 15 electrons. And then, whoa, what about the number of neutrons? Well, we know this mass number down here, 31, has protons and neutrons. If I subtract away the number of protons, that gives me the number of neutrons. Okay, so in fact, there's 16 neutrons in a phosphorus atom. Let's go back up to oxygen. Oxygen has 8 protons and 8 electrons. That's what this atomic number here tells me. But if I want to know the number of neutrons, I have to subtract 16 minus 8, which happens to be 8. Don't fall into that trap of thinking it's going to be the same. The number of neutrons can vary from atom to atom, even within the same element. Let's try fluorine over here. Fluorine with an F has 19 as its mass number and 9 as its atomic number. How many protons in a fluorine atom? 9. How many neutrons? Well, 19 minus 9 is 10 neutrons. And of course, there's 9 electrons there. So let's talk about isotopes for just a moment. Iso as a prefix means same. Okay, so that's a good thing to keep in mind. These are all atoms of the same element, and the examples I've shown you below are all carbon atoms. Carbon atoms all have the atomic number of 6. That means the same number of protons, which is 6. Now, the number of neutrons tends to differ from one atom to the next. So let's confirm that these are all carbon atoms. Look at the number of protons. They're all 6. So that tells me these are all carbon atoms. The number of neutrons here is different. That varies from one atom to the next. So it's like having 3 children, all with the same last name, the last name of carbon. But they have different first names, right? So that's how they vary. They vary by the number of neutrons. Now, if you add the protons and neutrons together, you get this number down here. Okay, so we add 6 and 7, we get that number. 6 and 8, we get that number. This is the mass of that particular isotope. And so if you back up and look at the periodic table for carbon has 6 and 12 in one of those boxes. That's because carbon 12 is actually the most common isotope. Sometimes you'll get like a decimal point on the periodic table. That's because they're averaging the isotopes, and one of these is probably more common than the other. So when you see carbon 12, that tells us the mass is 12. Now, knowing that the atomic number for carbon is always 6, you can figure out how many neutrons are in an isotope of carbon. So yes, these are atoms, but they are isotopes of the same element because they have differing numbers of neutrons, and therefore their mass number will also be different. Let's take a look here. How would you know that these are isotopes of an oxygen atom, or oxygen rather? Well, they all have 8 protons, right? That is our atomic number for oxygen. How do you know that they're isotopes? Look at that neutron number. Okay, that neutron number differs. On the left, we have 8 neutrons, and now they're showing us the isotope number there. 16 is the weight or mass of that atom. And on the right, we have 10 as the neutron number, so 10 plus 8 is, of course, 18. And again, that's the mass of that one. So these are isotopes, meaning they have the same protons, they have differing numbers of what? Of neutrons. And as a result, what is varying between these atoms? Is it the atomic number or is it the mass? It is the mass because that's what is housed here in the nucleus. Now, there are worksheets in your course pack for you to practice with. On the bottom of page 6 are some practice problems, and then a practice on 7 with answers on page 8. So I will send out answers to the bottom of page 6 to you.